Hello and welcome to Dare to Know, interviews with quality and reliability thought leaders. I'm Tim Rogers, and today we have a special interview recorded by Fred Schenkelberg in January 2016 at the Rams Conference in Orlando, Florida. Fred's guest was John Paschkewitz, Principal Consultant at Product Assurance Engineering, LLC. John has extensive experience in product engineering and management for new product development and sustaining engineering, both from an OEM and supplier perspective. He's a registered professional engineer and an ASQ certified reliability engineer. Fred talked with John about his experience and work as a consultant and his recent book, Next Generation Halt and Hass, Robust Design of Electronics and Systems, which is part of the Wiley series in quality and reliability engineering. Let's join Fred's interview with John Paschkewitz.
All right, welcome to Dare to Know. This is Fred Schenkelberg, and very pleased to be sitting across the table from John Paschkewitz. Hey, John.
Hi, Fred.
Now, you've done a couple of speaking of reliability shows with us, so you kind of got this podcast thing down a little bit. But you also do tutorials here at Rams, and so we're sitting in the hallway at Rams. You might hear it happening in the background. And I caught you kind of between sessions, and I believe your tutorial is tomorrow, if I remember right.
Yes, that's correct. Yes.
All right. So I don't think this will come out in time for anybody to do it, and likely you'll be back next year.
Yeah.
That's right. And so you've done the tutorials here a few times.
Yes,
right?
I have.
So, and if I remember from the program and from your interest and stuff, it's on accelerated testing.
Yes,
and you mentioned just before we started, it's not accelerated life testing, it's any kind of accelerated. So expand on that. What's the the abstract of that?
Today, accelerated testing is a vital tool because we've all gone to shorter product development cycles, less time. We just don't have time to do the old demonstration tests like we used to. So accelerated testing has become very much a part of product development.
Right.
And I advocate trying to do it early in the process so it becomes part of determining limits of the materials and components and so on that you're using in the product. Mm-hmm. So I start with, even during the design phase, using accelerated testing for reliability design of experiments. What a reliability DOE has is the response you're looking for is actually life under certain conditions of test, and you use accelerated conditions to compare different material or component configurations to see which produces the best result in terms of a response.
That's right.
And so you can expose it to stresses that you anticipate being there in the environment and then find the best combination of materials. So that's an early way to use accelerated testing in a exploratory part where you're trying to nail down the materials and components that you're going to use in your system.
Well, that sounds like it's really aimed at, early on it's on concept decisions, materials selections, vendor selection. Mm-hmm. You can start doing accelerated testing to help inform those decisions.
Yes, that's correct.
Okay.
The second part is doing an upfront risk assessment with a abbreviated form of FMEA. So you're looking at what is changed or new in this new product, because most products tend to be evolutionary.
That's right.
We're building on a technology or product base and improving it to meet some new needs in the marketplace.
Right.
And so we focus on those changes and unknowns, and that becomes the driver for your accelerated testing. And then we introduce tools like accelerated stress test or HALT methodology.
See, I call it discovery testing, or discovery process, because too many people want to pass the test.
Yeah, it's not a pass-fail test.
That's right.
It's finding the limits and margins of the product and which is the best one to use for this application. So the HALT methodology, you're defining those empirical limits of the product, and which is the most robust alternative, which is going to give us the best ability to handle the variability that we're inevitably going to get in the product. We're going to have variability in the way it's built. Manufacturer, you're going to get variability in the operating environment. So we need to have enough margin to do that.
That's right.
This kind of testing helps you find that.
And you cover all that and a lot more in this tutorial and other places.
The tutorial does focus on, it does have the DOE example, it has the AST HALT methodology, and also applying the HALT methodology to non-electronic products.
Right.
Again, it's a step stress methodology to find those limits, and then choosing the most robust alternatives. And those kind of tests are driven by the risks we anticipated in that upfront FMEA
risk assessment,
effort.
FMEA type stuff. But you've mentioned it a couple times, and I picked up on it right away. These are all aimed at decision making.
Yes, absolutely.
Right. So it's not the verification test
where not at all.
It's late in the program, and we're not making design decisions. We're making ship or no ship decisions, which are completely different.
Yeah, absolutely. This kind of testing is aimed at making robust design choices to get you the most robust product that's going to be most capable of providing the reliability that you need given the constraints you have.
Yeah. There's always constraints.
So
how do you get past the sample size question?
With HALT or AST, those kind of things, you don't really need a lot of samples. You need enough, like 5 or 6 is good. 3, you're starting to push a little bit, but you'll get an indication of variability from unit to unit. Here, we're not trying to statistically define a product life or anything. We're just trying to see which is most robust. So you need to do more than one in order to see, is there any variability, or is the first one you tested may have been on the strong side of the distribution.
Or vice versa.
Or the weak side. So you need to have enough to begin to see what the variability you might encounter, but you don't need a lot of samples at that stage. And you're not going to get them typically in early product development.
No. And the other issue is that, we're not done with the design yet. Why are you off running these tests?
The answer there is we're trying to help you make the right design decisions. And so getting involved early, helping select the right components and materials that are going to give them the most robust design and enable those trade-off decisions early when they can be made effectively. So it's a way to insert yourself as a reliability engineer in that early product development stage, which we're all trying to get into. We don't want to wait until, okay, it's all done, now go test it.
Now go add reliability.
It doesn't work that way.
No. Well, so in the tutorial, I'm sure you've had questions and people come up with stuff. Do you have any memorable questions or ones that made you think? Or
I think the ones that are the most memorable are the ones on level of assembly that you do accelerated testing at. And again, I think it's the shift from the mindset of verification kind of test where people are taking the final unit and trying to prove that it will meet the reliability requirements. And so you are used to testing at relatively complete products or large levels of assembly, and that doesn't work well. It's hard to accelerate the stresses you need when you have a complex assembly that's going to use a variety of different materials and components, and each one has different stresses that may be applied to it and so on. And you need to accelerate each one less in order to do the combined assembly. So it isn't as effective. It's much more effective to do the accelerated work at a lower level of assembly or component level even to prove out those components first, make the design robust, and then later on the verification tests.
There's the consideration though of the interaction pieces.
Yeah, that's right.
So hard drives and the quality of the power can affect the circuit board, and the mechanical systems can affect the response that you get on other parts. And so I can see where that's an argument.
Yeah, it's a concern. I think the thing that you're most looking for in the larger level of assemblies is maybe like beta level testing, where you're really focusing on those interfaces. Now that it's all assembled and in the operating environment, you're going to see things that really are hard to test in the laboratory.
Right.
And so what you're trying to
add customers to it, that really is hard to test in the lab.
Yeah. So the focus of this early testing should be just on getting the most robust choices in your design and making it as good as possible. And then when you get to the larger levels of assembly, then focus more on the interfaces and how all this stuff plays together in the operating environment.
So, you mentioned getting it as robust as possible or more robust and so on. Is there a measure for robustness? Robustability? I don't know if that's an ability or not.
Robustness is the general. There's a real good SAE publication on robustness. And,
okay.
I would have to look up the number of that publication, but anyway, it's about robustness. It introduces a thing called the robustness indicator figure, which I do put in my tutorial.
Okay.
And what you're looking at there is that's actually like a radar chart in Excel. And you take the spokes of the radar chart are the stresses that the product has to withstand.
So temperature, vibration,
whatever
voltage,
it happens to be is
it
applicable for this one.
Right.
And so the more of them there are, the more spokes there are, obviously.
Right.
And for each of those, you put on there what the target or the requirement is. And then you take your test results and put them on the same thing, overlay it. And it's a real good visual way to show the margin that you have in your product.
Okay, so if we're specified to say 40 degrees C, and we do some testing for some time at 50 degrees C, that spoke would be overrun.
Yeah, no, there's two plots on it. There's an inner one, which is your target or spec, and then the outer one, which is your actual test results.
All right, so hopefully everything's tested beyond.
Yeah, and if you got ones that are real narrow, hey, there's something we need to do.
There's not much margin left.
When you get into a design review, that's a good way to present it and show visually how much margin you do have. And the reason you want the margin is to handle the variability.
That's right.
The unknowns. You take the old stress-strength distribution and you want them as far apart as possible in order to minimize that interference.
Now, one issue I have with that is that I've seen it done so many times is they'll say, well, using temperature again, is we have a specification of 40 degrees C, and we're going to test to 10% over that, and then they stop. And so they'll exceed the spec. And usually it's on a sample and it's on a small number of, and just a short duration usually. On that visual, it'll show that it exceeded the specification. Is there anything wrong with, well, I think there's something wrong with just going to say 10% over.
That's not necessarily going to tell you the answer. So I advocate test to failure.
Good.
And that's
I can publish this now.
That's the objective of HALT and AST and those things, is finding those limits. When does it actually fail and how does it fail? You need that information. If you just do success-based tests, you know it did so well in a test, but is it going to fail in the next cycle, or is it going to take hundreds or thousands more? You don't know.
That's right.
You got to go to failure and understand the failure mechanism.
So if we had, say, an early test on a device, an item of a product, and we have 6 stresses involved, and all of them are tested beyond our requirements, our expected use conditions type things. Some are going to be way exceeding the requirements. Others are going to have a smaller delta between where they perform and where the spec is. Now that can inform your later testing in the verification area, because there you need to know the variability more precisely. But early on, we may not have enough samples to go for that. So
it lets you focus on, here's an area where we don't have much margin. We need to explore that more thoroughly.
That's right.
And then you can do it with more samples. So it kind of narrows down your follow-on testing.
All right. How about another question you may have fielded out of your students here in the tutorials?
The other one is probably on sample size, and I think we
that's
talked
a perennial
about that
question.
Yeah, that is, and they're always concerned on enough samples and the statistical significance of it, and so you got to cover that.
Well, some accelerated tests are really based on.
And I do include a tutorial, the traditional accelerated life test, where you are trying to quantify it, and again, that's got to be done kind of at the component level or small subassembly level, because it gets very complex. If you have more stresses, more levels to test to, it really expands into a very expensive and low test quickly, and you can't accelerate it as much because you're always limited by the weaker links in it.
That's right.
So it's difficult.
So in my practice, I've seen the sample size question comes up all the time. And I tend to use a sample size formula that's based on the binomial distribution. And it's based on trying to replicate some fraction or multiples of your life stress experience. And then it gives you a pass-fail criteria test to go back to it. I've also seen a lot of reliability textbooks and people using the chi-squared distribution, kind of using the confidence bound around I dare say, the MTBF value or failure rate, and use a chi-squared. Is there I mean, is there a recommended way to go after sample size? For the test that we need sample size?
There are tools, and I use ReliaSoft's Alta for accelerated life test analysis, which is a very nice tool, and it does have a test planning tool in it to help you determine sample size, which tends to be pretty conservative. So I kind of balance it with reality. Here you got a objective. Statistically, you'd like to have this many samples, but realistically, I can get this many. Is that enough to give me reasonable confidence bounds on my data?
That's right.
That I get it. So there's always a judgment aspect to it.
Now, if you use the exponential distribution with Alta, then you're basically doing chi-squared type thing. Yet the tool's got the ability to put in, if you know it's a log normal, if you know it's a Weibull, or you can make some assumptions there, you can get a tailored to these other distributions.
Yeah, and I've done that, and I found that most of the testing I've done, it's either a Weibull or log normal distribution.
Right.
And so and it's kind of a good part of the reason why your MTBF thing doesn't work is because the distributions are skewed one way or the other, and see the things that are based on a normal distribution don't work.
That's right. Yeah. Or the exponential, it doesn't reflect reality.
No, not really.
It's great in theory if you can test 100 items for an hour and you get 100 hours worth of value out of it.
Yeah.
No, it doesn't work that way. Why should somebody attend your tutorial, other than it's good to see them and they'll learn a lot? Who is the tutorial for?
I'm really trying to advocate the use of accelerated testing appropriately at the right times in product development, and especially accelerated stress test and the HALT methodology applied to products where people maybe have not considered doing that methodology, but it really can be applied and used with the proper stresses.
So why should somebody, what's the motive? So you get 2 hours in this tutorial. What would be a good reason for somebody to spend that 2 hours with you versus the many other options here?
Looking at the agenda, I think a lot of the presentations deal with modeling of various phenomena, and so this is a little different. There's only a few at the symposium this year that are on accelerated testing.
That's right.
And I think the approach I'm doing is kind of different than some of the others, which are maybe more focused on the quantitative accelerated life testing analysis, the traditional.
It's kind of an academic approach.
Yeah, so I'm taking more of a practical rather than the academic approach.
Yeah, and that's what I was going to mention, is that if accelerated testing, I mean, it's a huge field in and of itself, and if you want to get a good overview of it with a good practical approach to it, go to John's tutorial. That would be the way to say it. Well, thanks so much, John, for joining me for this. I'm not sure how much our audience can hear any of this with the background noise.
See how it looks.
All right, well, thanks, John.
Thanks, Fred.
Appreciate it.